the quality of my homework would increase if I use graph paper.
Okay.
Probably not.
Okay.
Wait, who's gone today?
Brooklyn.
Oh.
Now, I apologize in advance, I might have to take a phone call because it's an insurance policy with my mom who died in August. I'm fighting them, and they're supposed to call me back sometime, and so if I have to step outside, I apologize, but I've been playing phone tag with them for the last 3 days. And so,
You're good.
That
if they
sounds
call,
about
I
right.
don't want to,
You're fine.
yeah, I know I hate that, but
Do what you need to do.
I hate insurance companies. Okay. All right.
We should get rid of it and have Medicare for all.
No, this is like a life insurance policy.
UBI is
$1,000
Okay.
per month?
So we'll talk about the MGOH2 here in a little bit, what that means. Okay. So hopefully your graphs look something like this, okay? And as Anna pointed out yesterday, it said, hey, your maximum buffering is like 1 on either side of that pKa value, but that last one is 6, which is actually, up above that. So that one just, like I think you had done something like that, said, hey, here's your maximum buffering, that's fine, okay, if you have that. And like I said yesterday, the biggest thing is if you got a graph like that on the test and it said, hey, find the region of maximum buffering, just find the flattest part on that pH curve up to the point prior to where you reach that midpoint. Okay, so hopefully what you all saw, maybe not a drastic change because of the jacked up nature of our water, but here's what I want you to see, is that when you took that ammonium chloride, and this is the one that's been a little bit sketchy, and you add that to water, hopefully what you see is that water is acting as a base, and you're forming some hydronium ions and ammonia, okay? So what should happen theoretically on that one is that you should see the pH go down. Now that's assuming that you're starting at a pH of like 7. The water was already a little bit acidic because some of you, what was your initial pH, like 6.5, something like that?
6.9. 6.7. Ours were really solid.
Okay, all right, so it was already just a little bit acidic anyway, and so you might, and this is, if you go through the math, it shouldn't be that big a drastic change anyway. So anyway, so that's, you should, the main point I want you to see is that when you add that ammonium chloride, that pH goes down because you're creating hydronium ions. Now, in contrast to that, now I think everybody saw this happen. When you add that sodium acetate, okay, with the water, then you're going to form the acid C2H3O2 and some hydroxide ions, and that's going to make that pH go up because of the fact that you're reforming the acid and you're kicking out some hydroxide ions, and that pH should go up. Yes, ma'am?
Because isn't the water acting as an acid in that?
Yeah, the water's acting as the acid, okay?
So
Because that's giving up a proton, so that's a Bronsted-Lowry acid. So this is where water is what's called amphoteric, because it can be both an acid and a base depending upon the situation, okay?
And so it increases the pH because it's increasing the anion concentration?
With the acetate?
Yeah.
No, the only way, listen to me. The only way that you can alter pH is either changing the hydronium ion concentration or you alter the hydroxide ion concentration. Okay, that is the only way that you can alter pH. Because that's what that pH probe measures. The pH, we don't have a probe that measures anion concentrations. The only thing that probe measures is hydroxide ion concentration and hydronium ion concentration. That's it. Okay? So what happens is, you dump these anions in there, they react with the water, and it increases the concentration of those hydroxide ions. So your probe can't measure the concentration of this molecular acid because of the fact that it doesn't have free hydronium ions to interact. Okay? Yes?
Can we go over number 8?
Number 8? Okay, So, when you look, let's talk about what you should see on 5 through 7, okay? So when you go through 5 through 7, your pH on number 5 should be about 5, and your pH on number 7 should be about 6.5, okay? So there you go. Now, what's common to all of these is that you have a hydroxide ion reacting with the acid to form water and the anion, okay? That's what's common to all of these, right? So this still goes back to this idea of a system wanting to be in equilibrium. So no matter what, Mother Nature over here wants to create a situation where you have a Ka value for acetic acid, that 1.8 times 10 to the negative fifth, okay? That's what Mother Nature wants to have happen, okay? So that's going to be that hydronium ion concentration times that anion concentration divided by the concentration of the acid, okay? So that's your overriding theme. This is what Mother Nature wants to have happen, okay? So as you go down from 5 through 7, what happens to the concentration of your anions? It increases, right? Okay, but you still want that same Ka value, right? So you still want that same Ka value. So as the anion concentration goes up, what has to happen to the hydronium ion concentration to get that same Ka value?
Go up. Go down. Down?
It goes down. So you have a smaller and smaller concentration of hydronium ions. So as the concentration of your hydronium ions goes down to generate the same Ka value, what happens to your pH? There you go. Does that make sense? Anything else?
17.
Okay. So, calculate the ammonium chloride solution, right? So you start with your reaction, NH4 plus the water is going to field your hydronium ions and NH3, right? So, you've got this, the ammonia, right? But so when you look at your reaction, here's your rice chart. So this is going to start off as 0.2. This is going to be 0, this is going to be 0, just like you've done before, okay? Not a big deal. You can go minus x, plus x, x, 0.2. Now, here's the deal. You're starting with ammonium. You cannot find the Ka value of ammonium, okay? It's not there. But you can find the Kb value of ammonia. So find the Kb value of ammonia, use that to find the Ka value, and that's what this is acting as. So you're going to find that Ka value equal x squared over 0.2.
What should we approximately get?
For which one?
17.
Around 5.
Cool. Can we go for 19?
19 is the exact same thing.
That's what I figured. But,
Okay?
Yeah.
On 19, here's your reaction. You're starting with your acetate anion, right?
Mm-hmm.
It's reacting with water to reform the acid and hydroxides. But you don't have the Kb value for acetates.
Right. So yeah.
But you have the Ka value of,
How much should we? What should approximate to?
which one?
For 19.
Around 9.
AP labels next one.
What?
Did you finish your homework for it, or?
Talking about his hints on 19.
Huh?
Talking about your hints on 19, the literature.
I know. I thought you'd appreciate that.
Yeah, I did appreciate it.
Jason's a big Hamlet fan. So we all know.
Okay. We're good?
It's the order.
Anything else? Yeah, on those graphs with that buffered region, like we talked about, that's a little bit janky. Just find the flattest region. So, okay, going once, going twice, sold.
What order do you want things to go?
Basically, start with the blue sheet, or, excuse me, yours are different. Start with the yellow sheet, then the green sheet, and then the graph.
What about that?
Just staple that at the very end. Okay, they just called, I gotta go take this phone call, I'll be right back in just